Hello everyone, welcome to my channel. Our today's topic of discussion is a very important part of mathematics, that is the laws of indices. Now before going through the discussion, we must know what is meant by indices. Actually, this is the plural form of index. Now let's see how a number, a real number, can be represented in the index form. Suppose I am considering a real number. I am taking it in the form of a variable a. Right? Suppose a belongs to R. A is a real number. A into A. What will it give if I give you A into A? It will give you A squared. Right? Now, this is the index form. Here we get this A as the base and 2 as the index. And make sure that this can be represented, this can be written only if these bases are the same. Okay? Similarly, if we consider suppose A into A into A into A, how will you represent it in the index form? As A to the power 4. Here A is the base and 4 is the index. So this way, instead of 4, if we consider suppose A into A so on up to n times, then obviously this can be represented as A to the power n. Right? So here this A is the base and n is the index. So this is how we represent any number, any real number in the index form. Now let's discuss about the laws of indices. So representation of a number or a variable in the index form is clear to us. Now let us consider an example. Suppose in one bracket I am taking 2 2's in the product form, and in another bracket I am taking 3 2's. And all these 2 brackets are in the product form. Right? Now considering each bracket separately, we will get 2 into 2 means 2 square. Hope it's clear. And this 2 into 2 into 2 will give us 2 cube, means 2 to the power 3, as per this index rule. Right? So now if we multiply these two numbers, what will we get? 2 squared will give us 4 and 2 into 2 into 2 will give us 8. So we are getting 32 as a result. Now instead of considering these two brackets separately, if we consider all the 2's together, then what will happen? This 2 into 2 into 2 into 2 into 2 will be represented as 2 to the power 5, right? Because all the bases are the same. So obviously by this index representation, you can write it as 2 to the power 5. Now what will be the value of 2 to the power 5? Means what will be the result of 2 into 2 into 2 into 2 into 2? Obviously it will also be 32. So as the results are the same, we can conclude that this 2 squared into 2 cube representation is same with 2 to the power 5. And so we can write 2 squared into 2 cube equals to 2 to the power 5. That means 2 to the power 2 plus 3. Now the same thing can be represented in terms of the variable. So instead of 2, if we take A as a random variable and suppose the index is m into A to the power n, these two indexes are taken, which are the integers. Then obviously following this structure, we can write A to the power m plus n. Right? So this is the first law, that if the bases are the same, this is the mandatory condition, students, the bases must be the same. Then if the indices are different, suppose here it is m, here it is n in this structure, then we can represent it as A to the power m plus n, and this particular rule or law will be applicable for any number of such representation. That is, instead of this 2 a's, if we consider A to the power m, A to the power n, A to the power p, suppose these 3 different integers are taken in the power, then also it can be represented as A to the power m plus n plus p. And it will go, or it will be applicable for any number of such variables. Now let us explain another law. Suppose I am taking an example, right, like 2 to the power 5 division 2 to the power 3. So it is clear to us 2 to the power 5 is the dividend and 2 to the power 3 is the divisor. Okay. So we can write it as 2 to the power 5 by 2 to the power 3. Okay. Now this 2 to the power 5 can be represented as 2 into 2 into 2 into 2 into 2. And this 2 cube means 2 to the power 3 can be represented as 2 into 2 into 2. So if we cancel all these 2's, we are going to get 2 into 2 means 2 square. Right? Now how this 2 square can also be represented? It can also be represented as 2 to the power 5 minus 3. Okay? So here the calculations of indices are taking place. Here the result, the quotient can be represented as the difference of the two powers. That is difference of the power of the dividend and power of the divisor. Right? So now in the generalized form, we can get another law following this type of structure, that instead of 2, if we consider a, then a to the power m division a to the power n will give us a to the power m minus n. Right? So this is another important law of indices, that is a to the power m division a to the power n equals to a to the power m minus n. Here make sure students the same thing should take place, that the bases should be the same. Now let us consider another very important law, very useful law. Suppose you are getting an example, right, like 2 to the power 2 whole to the power 3. Okay. Now how will you represent this 2 to the power 2 in whole to the power 3? It can be represented as 2 square into 2 square into 2 square. Okay. Because in the power we are getting 3 as the index and the base was 2 square. Base is taken as 2 square. So obviously it can be represented as 2 square into 2 square into 2 square. Now considering each 2 square, we get 2 into 2 into 2 into 2 into 2 into 2. Right? Now how many 2's are you getting? 6 2's, right? Now look students, how this 6 can also be represented. This can be represented as 2 into 3. Okay? So 2 to the power 2 into 3 will also give us 2 to the power 6. So this is the law, that if you get this kind of structure, whatever be the base, it may be number, it may be variable, then here the powers will be multiplied to get the result. So here in the general form, we can write this law as a to the power m whole to the power n is equals to a to the power m into n. Another very important law. Now let us consider another important law. Suppose I am taking an example 2 into 3 whole to the power 2. Right? So obviously if we expand it, we know we will get 2 into 3 into 2 into 3. Right? So what will it give? 6 into 6 means 36, right? So 2 into 3 whole to the power 2 is giving us 36. Now, if we write it as 2 square into 3 square, 2 square into 3 square, then let's see what would be the result. 4 into 9, that is 36. The same result is obtained, right? So what does it mean? It means 2 into 3 whole to the power 2 is equals to 2 square into 3 square, right? So writing the same thing in terms of the variable, we can get another law, that is a into b whole to the power n equals to a to the power n into b to the power n. So here, as from the beginning we are taking a, b, the real numbers, this n, that is the index, is also a real one, and hence we get another law considering all these real numbers, that AB whole to the power n equals to A to the power n into B to the power n, and make sure students we can find the bases are the different, but the powers or the index were the same in both the cases. So this is another law, another very important and useful law of indices. So we have just seen that AB whole to the power n equals to A to the power n into B to the power n, and now where all the ABs were the real numbers. Now, if instead of this product form, we consider the division form, then what will happen? Let's say, suppose I am considering 2 by 3 whole to the power 2. So, this can be written as 2 by 3 into 2 by 3, right? So, we know this will give us 4 by 9. Clear? Now, if we consider 2 square by 3 square, that is, if the powers are written separately for the bases, then what will happen? 2 square will give us 4, 3 square will give us 9. So, same thing will happen here. Though it was in the product form and this is in the division form, but the same thing will happen. That we can write it as 2 by 3 whole to the power 2 equals to 2 square by 3 square. So, in the general form, we can write A by B whole to the power n equals to A to the power n by B to the power n. And here B is obviously considered to not to be 0. So this is another very useful law of indices. So we have learned many laws of indices, and in all those cases we have learned that in the representation, index representation, suppose I am considering A to the power n, where A and both are real numbers, n was taken a non-zero number, right? Now let's see what will happen if n becomes a 0. Okay, let's say this. Suppose I am considering A to the power 0. Here A is a real number, any real number. You may take any fixed number also, whatever it is. If the power is 0, then its value will be equals to 1. Okay. Here a very important thing must be remembered, that A may be any real number but should not be equals to 0. So the condition here is A not equals to 0, right? Because 0 to the power 0 is undefined. Okay. So any real number, if possesses the power 0, then its value becomes 1. Now considering this particular rule, we can derive another law. Suppose I am considering A to the power minus m, okay, where A and m both are real numbers. Now, A to the power minus m, let's see how we can represent it in another way, in another form. If it is A to the power minus m, then obviously in denominator we are getting 1. We can take A to the power m over there, that is 1 into A to the power m. Now, to maintain the balance, we are multiplying 1 A to the power m in the numerator portion. Now what will happen here? In the numerator we are getting A to the power minus m plus m by laws of indices. First law of indices, by A to the power m, it is kept as it is. Now in the numerator we are getting A to the power 0 by A to the power m. And something to the power 0, some real number, non-zero real number, I repeat, to the power 0 will give us 1. So it will give us 1, and in denominator we will get A to the power m. So here another law is derived, A to the power minus m equals to 1 by A to the power m. So what will happen? How we can represent 2 to the power minus 3 for an example? Suppose I am telling you 2 to the power minus 3. So how will you represent it in this way? 1 by 2 to the power plus 3, right? So these two are very important, another two very important laws of indices. Now let's derive another law. Suppose we have A to the power m equals to B to the power m, where positively A is not equals to B. Then we can represent it as A to the power m by B to the power m equals to 1. That is, we are dividing both sides of the equal sign by B to the power m, right? So here we get A by B whole to the power m equals to 1 by one previous law of indices, what we have already learned. Now we have seen that any real number, if in any real number we get the power 0, then the value becomes 1. And here the base is a by b. Positively b is a non-zero number, right? So here the base is a by b. So if we consider a by b whole to the power 0, then the value of that particular representation will also be 1. So in the place of 1, we can write a by b whole to the power 0, isn't it? Okay. So now if we compare both sides, in both the sides of the equal sign we will get the bases are the same, a by b, right? Only the powers are the different. Moreover, we are getting from this representation that a by b whole to the power m is equal to a by b whole to the power 0. So obviously, the only condition what we get by comparing both sides of the equal sign, that m is equals to 0, right? So here another law is derived. If a to the power m equals to b to the power m, where a not equals to b, then m is equal to 0. Another very important law of indices. Now let's try to answer one question. Suppose I am giving you 2 to the power m equals to 2 to the power n. And I am telling you to find out two such values of m and n, for which 2 to the power m becomes equal to 2 to the power n. Can you find them out? Just pause the video and think over it. Yes, I hope you all have understood that 2 to the power m will be equal to 2 to the power n only when m equals to n. Because there are no such distinct values of m and n for which this type of equation be satisfied. So if the bases are the same but the powers are different and the two expressions are related by equal sign, then it implies m is equals to n. Okay, so in general form we can get another law of indices, that is a to the power m will be equal to a to the power n only when m equals to n. Another very important law of indices. So in today's class we have learned many laws of indices. First of all, we have learned a to the power m into a to the power n equals to a to the power m plus n, where the bases must be the same to apply this law. Then we have learned a to the power m division, a to the power n equals to a to the power m minus n. Here also the bases are the same. A to the power m whole to the power n gives us a to the power m into n. ab whole to the power n gives us a to the power n into b to the power n. Okay, and then a by b whole to the power n, where b is considered to be non-zero real, gives us a to the power n by b to the power n. Then we have seen that if the power of any non-zero real number be 0, then the value becomes 1 in all the cases. And then a to the power minus m can be written as 1 by a to the power m, where a is a non-zero real. A to the power m equals to b to the power m gives us m equals to 0. Okay, where a is not equals to b. And finally we have got that if a to the power m equals to a to the power n, then obviously m is equals to n. Okay, if both of them are 0, m and n are 0, then both the values will be 1. But other than also, if they are non-zero numbers, non-zero reals, then in those cases also we will find m should be equals to n. So now please go through all these laws. In my next video, I'll discuss about the applications of all these laws. Till then, take care, stay safe.